Welcome back to another episode of Quick Chemistry. This is Balancing Chemical Equations. If you're unfamiliar with what chemical equations are, I strongly suggest watching my Introduction to Chemical Equations video before launching into this one. So we know that in chemical equations, mass can neither be created nor destroyed. This means that when we're writing chemical equations, we must always have the same number of each kind of atom on the reagent side of the reaction as we do on the product side. Here's my generalized method of balancing equations. Say that we have the equation a plus b forms a2b3. To balance my equation, I first draw up a quick table with 3 columns. I write down all the elements that appear in my equation down the left-hand column, and I label the 2 rightmost columns R for reagents and P for products respectively. Now I start a tally of how many of each element I have on either side of the reaction. If I'm writing this on paper, I'll make these markings in pen. On the reagent side, I only have 1A and 1B, so I'll tally that in. On the product side, I have 2A and 3B, so I'll write that down as well. I'll now switch to using a pencil, so that if I make a mistake with my multiplication, I can always erase it and start again. Now in order to get to 2A on the reagent side, like I have on the product side, I'm going to need to double the amount of A that I have by writing a 2 to the left of it. Because I now have 2 A's on the reagent side, I'm going to mark that in my tally. Now let's turn to balancing B. I have 1 B on my reagent side and 3 on my products. I'm going to triple the number of B that I have on the reagent side by writing a 3 to the left of B and mark that in my tally. Now, if we look at my tally table, we can see that the number of atoms of each element on the reagent side of my equation equals the number of atoms of each element on the right side, the product side, so we now have a balanced equation. Note that if we only have a single reacting molecule, or if there's only one kind of atom in a given molecule, there's an implied coefficient or subscript of 1, but we don't write this in. One last thing to note is the difference between the coefficients of A and B, which are the numbers I multiplied them by to balance the equation, with the smaller, subscripted numbers to the right of A and B in my product. The subscripted numbers represent the fixed ratio of A and B in the product molecule. We can't change these numbers, since doing so would change the identity of our product. All we can do is multiply the number of reagents or products by some number, or some coefficient, like I've done on the reagent side, in order to balance the equation. Let's now look at some examples of balancing equations. Here's the unbalanced reaction for the complete combustion of ethane to form carbon dioxide and water. If you'd like to try this out by yourself first, pause the video here and resume it when you're ready to check your answers. Let's start by drawing up our table and putting in the number of each kind of element that we start with. On my reagent side, I have 2 carbons, 6 hydrogens, and 2 oxygens. On my product side, I have 1 carbon, 3 oxygens, and 2 hydrogens. Let's first balance our carbons. To do this, I'm going to double the number of CO2 on my product side and obtain a total of 2 carbons on my product side, same as the reagent side, and 5 oxygens on the product side, which is fine to have for now. Next, I'm going to balance my hydrogens by tripling the number of water I have, giving me 6 hydrogens on both sides, and leaving me with 2 oxygens on the reagent side and 7 in the products. To balance oxygen, we can use a little trick which only really works for O2. Since O2 is just made up of 2 oxygens bonded to one another, I can look at the number of oxygens I need in total on the reagent side, in this case, 7, and I can write 7 on 2 in front of oxygen to balance it out neatly. This little trick with oxygen works for all combustion reactions, since in a chemical equation, combustion is just the combination of fuel, such as ethane, with oxygen. Let's look at another reaction, the neutralization of sulfuric acid with sodium hydroxide. Since this is an acid-base reaction, a salt, Na2SO4, and water will be produced. I'll give you a second here to pause and work through the question yourself if you'd like the practice. We'll start again by drawing up our table and tallying up the number of each kind of atom we begin with in this unbalanced equation. You may first notice that the number of sulfur and oxygen atoms are equal on both sides. While that's great, our aim is to balance the entire equation, so it's okay to unbalance some already seemingly balanced bits in order to achieve this. Let's first look at balancing our number of sodium atoms. This is easily done by doubling the number of sodium hydroxide molecules in our equation. Next, to balance our hydrogens and oxygens in one fell swoop, we're going to double the number of produced water molecules. And there you have it, a perfectly balanced equation. Let's go through one last example before we wrap up this video and take a look at the fairly violent reaction of cesium with water, which produces cesium hydroxide and hydrogen gas. Again, I'll give you a second to pause here if you'd like to run through this example yourself before I talk through an explanation of it. To start, as always, we'll begin by drawing our table in and by writing out the number of elements we have on either side of the unbalanced reaction. On the reagent side, we have 1 cesium, 2 hydrogens, and an oxygen. On the product side, we have 1 cesium, a single oxygen, and 3 hydrogens. It would appear that for this equation, the only thing we need to do right now is balance the number of hydrogens that we have. Since we can't have fractional values for H2 like we can for O2 here, we're going to have to double the number of water molecules as well as the number of cesium hydroxide molecules to get 4 hydrogens on either side. While this also doubles the number of oxygens on both sides, that's completely fine since there's still an equal number of them on either side of the equation. The only thing that's unbalanced now is the cesium. That's fixed by doubling the number of reacting cesium molecules to give a perfectly balanced equation. And that's it for this video. Be sure to like, subscribe, and comment down below to let me know if there are any other concepts you'd like to see me cover, or any other equations you'd like me to balance. Until next time.